My name's Robert Ristroph. I've been doing stuff with 3D printing for more than 10 years. And this is a short overview of the very practical side of 3D printing, like not so much the action figures and so on, but making useful structural things like you may do in the course of astronomy. I put my email address and a web page there of a little makerspace that I and Jim showed there run. And so my slides are mostly bullet points of a number of points I want to run through, and then this is going to be a short presentation, and afterwards circle back to me about particular things. I've been talking to a few people pre the meeting, and I think there's a wide variety of people who in their expertise and so on. So just a quick overview of 3D printing. The additive manufacturing is like a lot of things. It kind of had a slow start in the big institutional era and Defense Department projects and so on. One of the first 3D printers was here at UT with a professor named Carl Deckard. And around 2006 to 2013, there started this explosion of hype about it and a huge amount of popular interest, and then it kind of tapered off and plateaued a little bit as things do. And the online sort of consumer community of it tends to be kind of dominated by printing consumer type things. So I think the average 3D printer person out there mainly downloads files off of some service and prints them without modification, except for maybe scaling them bigger or smaller. And I would like more people to actually manipulate their designs and so on, for it to be a kind of an entry point of people into programming and manipulating the world in general. And I think among sort of the popular perception, the general perception of 3D printing plastics is they're weak and crumbly and stringy and so on, which is often true. But with relatively cheap equipment, like not having to go to some giant corporation with tens of thousands of dollars, you can print things that are surprisingly strong, precise, and replicable. And let me see what else I have here. I want to give a quick overview of the materials. I think everybody who knows a little bit about it probably recognizes the common materials. PLA is a plastic that melts at a lower temperature, but tends to be more stable. And the astronomy area, you might be interested in it because it doesn't shrink and expand as much with temperature as some of the other ones. ABS is a very common plastic that is a little more robust, but has more temperature movement. I mentioned TPU there because a thing that many people are not aware of is there are flexible rubber-like stuff, and that's actually the only samples I remembered to bring was some flexible stuff that I had printed on a rubber-like material. That comes in useful for printing mounts to something fragile, feed on things to isolate vibration and seals and so on. When you get into, I think there was some sort of pre-discussion about how far you could push 3D printing in terms of strength and stiffness. And you can design into these fairly ordinary plastics a lot of strength and stiffness. But if you really want to push that limit, polycarbonate is probably the stiffest and strongest plastic that's printed by heating and extruding it through a little nozzle. And there is a formulation of it that's sold by an Austin area company up in Pflugerville that has chopped carbon fiber in it, which is usually problematic to print because the little carbon fibers, sand the inside of your 3D printer basically and wear it down. But they they have some kind of way they put all the fibers in the center of the strand until it goes out and mixes. And they have a setup where they print, you can print off a consumer level 3D printer, polycarbonate with something like close to 50% of its volume being chopped carbon fiber. And it's a extremely stiff and strong material. And the carbon fiber, which is, not oriented, it's all throughout it like a felt. But it keeps it very temperature stable. A lot of these plastics are also not humidity stable. So if your telescope collects dew at that point in time, plastics can swell. This is pretty stable stuff. It's like pretty interesting to hold in your hand. I wish I had some to show you. The carbon fiber wicks away enough heat that it feels cold in your hand like metal does, for the same reason metal does. So, but it is very finicky to print. I would recommend, if you're looking at trying to push the boundaries, making a telescope or something, print your things at a PLA and get the shape and size right and make sure that they work. And then if you need to, find someone with an exotic printer and you can get it done out of something. I see a hand up in the back there.
I have a printer of my own and some friends that do printing. If I remember right, the carbon fiber PLA will also abrade the inside of the nozzle more quickly, correct?
Absolutely. And the special stuff that I mentioned, they're kind of secretive about it, but I think what they do is they make the filament by having a sheet and put the carbon fiber in the middle of it and roll it around it. So when the filament goes through, it's just a plastic touching everything till it gets to the nozzle.
Right.
But it's still going to abrade the nozzle itself, and it is like printing sandpaper. I mean, it will sand that away. That's great. Let me shoot. Forgot what my next slide is. This is just a quick mention, kind of at the bottom end, like if you were getting started into 3D printers, kind of how accessible it is. There are printers that'll print about 6 or 8 inches a cube for around $180 that are pretty reliable. If you are willing to double that, you can get this new brand called Bamboo, which is extremely reliable and friendly to new people. And it also prints really fast. If that's in your budget, that's what I would recommend. There's actually a store here in Austin out on Bee Caves that's also where you can go and look at them and manipulate them before you buy them.
Yep,
and maybe do a test print.
MEP
What's the name of that?
changed all their sheet numbers to get rid of the
If you
dots
look up,
in their sheet
I
numbers.
don't remember, but if you look up 3D printer store Austin,
Okay.
they're in the news because they opened recently,
and
they're the
we didn't
only
have
ones.
structural sheet numbers.
So and they will also print stuff for you
All
on
right, I've
a
taken that
commission
out.
basis.
I'll
So
update the
if you
index.
figure out something and then it's bigger than your printer, or you don't want to mess with that step,
Sure
you
thing,
can
YouTube. Thanks.
just pay them to print it. And they also do some of the more specialized materials. This slide is kind of a starting point maybe for more a talk after the meetings, like what actually makes sense to 3D print. And I guess the main points I would make is the first and most useful thing a practical person with 3D printing usually finds is not making the end parts, but making jigs to hold something to make the end parts. Almost all woodworkers who use it end up printing a lot of strange little corner jigs and stuff like that. However, the accessible stuff you can print now is big enough beds and strong and stiff enough to actually make structural members, mounts, say things that have gears and stuff like that. I have printed threaded parts, both with the threads in the plastic and by doing a heated insert. So you essentially take a nut, heat it up on a soldering iron and press it into the plastic to give yourself a little metal threaded mount point. There are some things that the 3D printers are generally not good at. Their surface finish is not good. And just because I know somebody's gonna ask, I did once attempt to print a lens out of clear plastic, and it was not impressive. It was frosted essentially. And the soft parts are the surprising one that people often don't think about. So there's 4 books. Yes, I have a hand up here.
What was the limiting factor on the lens?
The limiting factor on the lens was having the layers adhere enough that they were optically clear. There was
Okay.
little tiny bubbles in there, which essentially made it like frosted glass.
Yep. Okay.
And if you annealed it afterwards or kind of printed it extra hot, you could
Mhm.
kind of get it there. So it was a lens that was of the quality you would get on the cheapest flashlight you ever bought, like that kind of level. And there's also a hand up in the back there.
If you're printing something where the surface finish matters, resin printers will give you a better surface finish. It's still not gonna print a lens, but they will give you a much finer surface printed finish with not such obvious layer lines.
Yeah, SLA printing.
Yeah, that's definitely true. I've done a little bit of resin printing and also as a experiment, I did print some eyeglasses on a resin printer once. The finish is not appropriate for astronomy. It might be appropriate for like a hand magnifying glass or reading the fine print or something, maybe. But in general, like light carrying stuff out of clear plastic, you can kind of do light pipes to route the light of an LED to where it's exposed on the outside of an enclosure. And a few things like that, and that's about as good as you can get. Otherwise, you're gonna have to polish and smooth it. And plastic is not as amenable to that as other things. You can kind of make it look pretty by flame polishing it, but you can't do anything exact. So there's a book circulating around. Well, there's 4 books circulating around. The green one there that there is particularly good. The title of it is Functional Design for 3D Printing. And I think it will give you a lot of ideas on how to structure your print so that you can get it to be strong. It goes over FDM 3D printing will have a grain. The layers go in a certain way. Its weakest part is separating on the grain. And it goes on to a number of different tricks, like often printing a solid piece is not the strongest thing you can do. If you print it so that it's 50% infill and then give it very thick walls, that's usually better. And if you need strength in a particular area, if you put like little pinholes in that direction, then that forces the printer to make walls and little cylinders in that direction. And you can play some tricks there so that if you want something to be very strong in compression in one direction or temperature stable in one direction, you can make sure there are no long contiguous pieces of material in the direction you want to always be stable. So there's some nice stuff there. I want to hit a couple of little software demos before I pass this off. So I'm going to keep going. Yeah, so this gets into the basic, the kind of 3 things I wanted to show you for almost everybody doing anything with 3D printing. Often it's the first thing they've ever done where they put their idea into a computer and then it came out of the machine instead of, say, starting out with a piece of paper or a sketch on a piece of plywood or what have you. And you will almost inevitably find out that that is the hardest and most frustrating part. You can have something you can vision in your mind as pristine and you just can't get it into the computer enough that it can take over the rest of it.
Yeah.
The top 3 things here that people use for designing stuff, the easiest one to use and learn is probably Fusion 360 because it's heavily documented on YouTube. It is not free and you have to be connected to the internet to use it. And but it's kind of a standard in certain areas. This next one, FreeCAD, is open source. It has gotten a lot better and it had a horrible reputation for a learning curve for a long time. And it now only like half earns that reputation, but it's still there. But it is amazingly powerful and free, and you don't have to worry about some company going bankrupt. You can't get to your designs and so on. And then the final one there is something that probably works for a lot of functional things like building brackets and jigs for holding things. it is open source, but it uses a simple little coding language to describe the shapes and then render them, and you can export them to send to the 3D printer. And yeah, I'm just going to, I kind of find my presentation here, and I have these other things open. Maybe I'll start with this OpenSCAD. Keep you an idea of my time. I'm gonna give like a minute or two to each one of these things. So the text here is unfortunately kind of small, but here you can see a box that has a thin flexible hinge, allows it to snap shut. And there's at the top, there's a long list of just variables being set. So this is parameterized. So I can render this box into different shapes and sizes and thicknesses. And this program will automatically, when it sees these variables, make this little form over here so that I can just enter in the new things and hit render and not, and it will reset those variables. And I'm going to try to zoom down here to something. So here is sort of a nested series of things here. You can see one of the primitives, which is a cylinder, and then there's a translate, which moves it to a certain position. And then it repeats that for a certain number of things with a for loop. And then this hull says, wrap that resulting thing in like a sheet. And here there is a rectangle, and one is being subtracted from the other to make a whole. That's what the difference is. And here is a couple of things being unions together or joined. Don't be intimidated by this. It's actually pretty simple to learn. And for whatever reason, I guess because the way it was changed, ChatGPT knows this very well.
Huh.
If you tell ChatGPT to give you a box in OpenSCAD with holes that match a certain stepper motor, like it'll be pretty close. Let's see,
I have a question.
Yes.
When you're done with it, what does it output? An IGES file, step file?
For most of the 3D printing workflows, which you, FreeCAD tends to put a step file, which is the standard interchange for CAD files, but to go to the next step of 3D printing, you have to make an STL file, which is,
Well, not all printers should be able to take a step file then, shouldn't they? Don't they?
most printers don't take a step file, they take an STL file. And so it's lost kind of the design history, and it's just a collection of
I know
facets
what an
described
STL
in-
file
yeah,
is, but
okay,
so does it OpenSCAD output a STL then?
yes.
Okay.
And FreeCAD can also, here's FreeCAD, as you can see, it's a bit more of a traditional CAD program. Over here, it will have a tree of parts as you built it, and you can have it highlight and display different parts. And the last thing I was gonna pop up was the actual slicer program, but I don't think I actually have that up. And I think we need to leave time for the next person. I'm gonna start this and see if it pops up, but maybe the next person.
You've got 10
should
more
start.
minutes.
I think we're
Oh,
squeezing in
we're-
one more person.
Okay.
You want to start setting up, because this is the last thing I was gonna show, if this thing will pop up. Okay. Okay. Okay, and so when you have that STL file, this is a slicer. Let me find something recent that I sliced. So this was some eyeglass frames. And so you have a piece of software where you can import your STL, you can scale it and move it around and change its orientation to get the layers as you want. And and it also has a huge number of settings here in terms of your layer heights, and if you wanted to use a different temperature for different parts of the print, and an incredible amount of different stuff. And I want to do the preview here and zoom in, and my pinch on this pad is horrible. Let me yeah, well, there it goes. So I'm zooming in here And I doubt you guys can see that very well, but it's essentially showing the individual path of where the nozzle will go, what they would call the tool path in machining. And this thing is, I need my other mouse, which I think oh, wait, I did bring it. All right, let's see if this will. There we go. So we can zoom way in. So I'm changing what layer it's at, but here in these little highlighted spot, it's showing you that for that layer, it's going to do the red, then the green, then the yellow. And let me move to a different layer. And you can see this little ghost showing you where the tool head is. So you can kind of vision where it's going to go to squirt out that plastic. And you can set it to use different temperatures for I think the red is plastic that will ultimately be on the outside of the part. So you could set it to do something else there. And over here, if I move the zoom controls, I can go to different layers and you can see that infill.
Unless you want to come home and we can.
And this is a concept that translates well over to CNC machining, the idea of inspecting your tool path and tweaking it and so on. 3D printer people almost never like hand edit their tool path or tweak it that much. They kind of generate it, inspect it, and then regenerate it again. So but that's kind of the general tool path for trying to 3D print something. You start with that OpenSCAD or FreeCAD.
That's why I thought you meant
you make your part, visualize what it's going to do in here and print it, and then it doesn't quite fit, and you iterate far more times than you will anticipate for sure. So I think that covers everything I was going to cover. So should we pass to the next person?
Okay. Yeah, I know.
Testing, and everyone hears me? All right, so, yeah. Hi, I'm Anshu, member of the AAS for a bit more than a decade now. And some of y'all might remember me as the baby-faced kid who joined with a passion for astronomy so long ago. I think I've lost the baby face, but the rest of it's still here. Like Joyce said, I recently graduated from UT Arlington with a degree in physics and got the opportunity to do some research. Before I get into that, I just want to thank all of y'all for being here, for keeping my passion in astronomy up, all that, for giving me a scholarship when I originally got into college. And I want to thank Joyce for giving me the opportunity to present to y'all and show y'all what I've done. So, not to what I want to talk about. I had the opportunity to do some research when I was at college on trying to detect exoplanets with radio imaging. Before we get to that though, let's go over a little bit of background. What is an exoplanet? I'm sure y'all know what an exoplanet is, right? It's a planet outside our solar system, more or less in two types. And there's about 5,800 of them last I checked a couple of days ago. When doing research on these, though, you tend to split them up into these four types, more than the two I showed earlier. 3 of these are in our solar system, and 1 is not. So let me go through what we're looking at, what we see, all that stuff. First type of exoplanet we look at is gas giants. This is the one I personally looked at when I was doing research. This is your basic Jupiter, your Saturn, that type of planet. You get some special cases that are really close to a star, called hot Jupiters. But more or less, these are just big gassy helium hydrogen balls with a metal core. You also have your Neptune-like planets, again, pretty simple, right? It's like Neptune, methane, helium, hydrogen, a little bit of a smaller planet, but still pretty similar. You have your terrestrial planets, this is your Earth, your Mars, your Venus, small, rocky, dense, usually has some type of land on it. And then we get to the fourth type. This is a little bit more interesting. We don't really have an example of this in our solar system to talk about. But these are super Earths. They're kind of halfway between the size of a terrestrial planet and Neptune. And since we don't really have one in our solar system, we don't really have a good understanding of what they could look like. Could be more like Earth, they could be more like Neptune with a thinner atmosphere. We just don't know. There are 6 main methods that we traditionally use to find planets. These are radial velocity, astrometry, microlensing, timing, transits, and direct imaging. Radial velocity involves looking at a star and seeing small shifts in the red and blue wavelengths as a planet orbits around it to figure out, hey, there is something going wrong here because the star's moving a little bit. Similarly, astrometry is looking at the slight wobble in a star's position to see something's going around. Microlensing involves gravitational lensing when something of a huge mass passes in front of a star we're looking at, which can give us a huge boost to seeing whatever's behind, whatever's around that star. We also have the timing method. With the view of the looks like the planets going around pulsars or trying to detect a second planet in the system. This is when you're looking at the timing of an existing planet or a pulsar beam and seeing if it shifts a little bit this way and that way because of another planet orbiting. We have the transit method. This is the one in the GIF here. You can see as the planet is going around the star, at some points it passes in front of the star and the light from the star dips. This is the one you guys might be familiar with. It's the one that people use with JWST to find exoplanet atmosphere, stuff like that. And finally, we have direct imaging, which is taking a picture. Pretty simple, right? Now, one thing we might have noticed is all of these methods, aside from direct imaging, look at the star and find planets at the time. What my research was on is trying to find a new method of detecting exoplanets that looks at the planet itself, the radio emissions coming from the planet, and trying to find it that way instead. For my research, I used to spec up the Square Kilometer Array Telescope, the SKA telescope, which you can see in this picture. So I mentioned we're looking at radio emissions, right? But before I talk about radio emissions from exoplanets, let's take a step back. Let's look at Earth. Now, I assume all of you have seen some diagram like this, something like that, yes? Earth's magnetic field and solar wind. Pretty standard stuff, right? Now, how the solar wind works is that electrons that are thrown off the sun interact with the magnetic field of planets like Earth, and they spiral down to the poles of the planet, and they cause stuff like the aurora, right?
Yeah.
Well, the same process can also create radio waves. This is what we call auroral kilometric radiation, or cyclotron laser radiation. About 1% of the total energy carried by the solar wind into these poles creates these radio waves above the Earth's atmosphere. And this is the strongest source of planetary radio waves we know. I've been told, any of you guys have ham radio experience, telescope experience? I've been told if you point a ham radio at Jupiter with the right frequency, you can detect Jupiter's auroral kilometric radiation just with that. Sure, if this will work, but here's a video of what it sounds like from. Yeah. Online, I'm not sure if that comes to. Hold on, let me fix that. Sorry. For everyone online, I'm not sure if that came through very well, but if you go to the link, you can see here, you can listen to that yourselves. So, why are we looking at this type of radiation? Well, like I said, it's the strongest source of planetary emission globally. We've detected in solar system planets pretty easily. Like I mentioned, Jupiter, we can also detect Earths using telescopes and satellites outside the atmosphere. And finally, we can also use this to find information on the magnetic field of this planet. This means we can find information on the interior, like what's generating the magnetic field, what's inside the core, stuff like that. And combining this with data, like I mentioned, from JWST's atmospheres detections, we can get a full overview of what a planet's going to look like, what an exoplanet's going to be like, before we even get telescopes advanced enough to properly see the surface. Now, how is it detected? I guess y'all have seen this equation, right? The Drake equations. People think it's complex, people think it's confusing sometimes. Here's the equation I use. Now, I know it looks a lot more complex, it looks strange. It's not that bad, we can go through it step by step. First thing you need to know is when we're looking at this mission, we're looking at the strength in chance. This is a measure of radio flux density, it's how strong we're getting the signal. This first term here, you can see 4.6 megajoule. All right, first variable. This is the planetary rotation rate. This is how fast the Earth spins or the exoplanet we're looking at spins. In this formula, it doesn't really matter. We'll get to why when I get to the results, but right now you can just kind of imagine this term as one. The next couple of terms are pretty similar as well. This is the ratio of the planet's mass to Jupiter's.
No, it's always over there. This is the Washington Turnpike.
Ratio of the planet's radius to Jupiter's. And this is one of the more confusing terms in this one. This is the beaming solid angle of motion. It's measured in steradians or spherical radians. And this is basically how much of that emission is actually coming toward us, toward our telescope. After that, a couple more simple terms. The distance the star is from us, this is measured in parsecs. The distance the planet is from the star at the furthest point in its orbit, this is measured in astronomical units. And then two terms here, which are basically talking about the properties of the star's solar wind, which interacts with the magnetic field. This is the stellar ionized mass loss rate, which is how much of the solar wind is actually ionized. For a lot of stars, it is 100%, but not for all of them, so you do have to put this into account. And we also have here the terminal velocity of the stellar wind, the fastest the particles reach when they're moving through and into the area that magnetic field can catch them. This we can calculate using the radius and mass of the star. So what have I done? I took NASA exoplanet database, filtered out all the values that aren't published and confirmed, which means anything that hasn't been confirmed to be from an existing exoplanet. I set the planetary rotation rate and the beaming solid angle of immersion terms to 1, and I plugged it into that formula to see what the radio flux density we would be getting from each result is. I also gathered the average values of the stellar ionized mass loss rate from multiple sources. We don't have a good formula to detect what type of star, how much of this is going to be ionized yet, so I just plugged in some average values I found. And I calculated the detection threshold of the square kilometer array telescope to see, okay, which percentage or which parts of this could be detected through that telescope. Here you can see a table. This is how much you would need to detect at each band the telescope is looking through. So the results I got from this, out of all 16,000 values in the database, some of these are repeat values. This is why that's more than the amount of confirmed exoplanets. 83 of those values gave me a calculable flux density. So 83 numbers I got out at the end. Out of those 83, 4 potentially were detectable by the telescopes that I put in. 3 of these planets are hot Jupiters, and 1 is potentially a brown. I mentioned potentially because currently the error bounds of where a planet turns into a brown dwarf are kind of hazy. I've seen papers talking about as low as 12 Jupiter masses and as high as 25, or where that boundary is. This potential brown dwarf has a mass of about 18 times that of Jupiter, so it's kind of smack dab right in the middle, which is why it's potentially.
That's our speed.
It orbits approximately every 14.5 days at a distance of just less than 0.1.
Good. Yes, sir.
The other 3 planets
Want
here
you to take this
are
and revise
the
back
same type of
down
stars.
round.
They have lower masses that put them squarely within hot Jupiter territory. This one is 2 3/4 Jupiter masses, which orbits with a period
Yes or no?
of 13.
Here's the way to have
days.
to. Watch it.
These planets orbit
And listen.
faster at around 2 days each and have higher masses, 6.1 and 7.2 Jupiter masses. And as published, I'm happy to announce I'm a co-author on a paper talking about these results and what we could do using the SGA telescope once it's fully online. What's next? Well, next I plan to calculate these thresholds, other radio telescopes, see if we could get better or worse results from them. Try to find a formula for those missing terms I talked about before. And try to find a difference between the observed and calculated flux density for solar system planets to see how far off the calculated flux densities I could have gotten were. Finally, once the SKA telescope is fully online, eventually we're hoping to get some time at that telescope to see.
Thanks to Mr. Racist, we now meet again.
And that's all I have. Thank you.
Let's form that your surrender. Once more, sir, you are interested in supposing that I can be taken against my will. That's our final answer.
I would be able to like do the
prefer
Earth-like
to
planets
die.
versus the hot Jupiter type planets.
Eventually, yes, currently our telescopes just aren't strong enough to pick up anything from the Earth-like planets.
Question about your formula. Back in the 70s, Dr. Han Solo said that parsecs were a unit of speed, not distance.
Common misconception. Parsecs are a unit.
Yeah, I know. Yeah.
Like Dr. Han Solo. Because it was light years ago.
Yeah.
3.26, as a matter of fact.
Questions? Let's say thank you. Research.
If you think about humanity, antiquity, those people were the same as we are. They asked a lot of the same questions, I am sure. What is out there? What is the past, the future of everything? And they had creation myths. And the thing that's different now is that as of 100 years ago, following the work of Albert Einstein, we have our own creation story. It's called the Hot Big Bang. But the difference is that it's correct. It's incomplete, but it's correct. And that's pretty amazing if you think about it. So in human achievement, that's a really big deal. Well, so historically speaking, the origins of modern cosmology began with Einstein, and his work was followed up very soon after by others who took Einstein's equations and applied them to the universe as a whole and realized that there are 3 possible evolutions for the universe. It could be expanding, contracting, or static. These are solutions to the equations. And Einstein really liked the idea of a static universe because that's extra symmetry. It's the same at all times. But on the average, but along came Edwin Hubble and showed that, well, the universe is expanding. He was working at the Mount Wilson Observatory above Pasadena. And actually, it's also kind of amazing to think that at the time of Einstein's amazing theoretical work, observational astronomy was still quite primitive. People thought that everything that you see out in the sky was all part of the Milky Way. And it took Hubble to convince people that things are way too far away for that to be true. And they had started talking about island universes. Well, we know there are galaxies. There's a lot more out there. The other thing that he proved, as I said, is that the universe is expanding. And the way he did it was look at distant galaxies. And if there is stellar light emissions of atoms, and you know the properties, you know what atoms there are, and you know what wavelength those atoms are emitting at. But then you measure those wavelengths today, and they're longer. It's kind of like a balloon. You draw a wave on there. So that's the emitted light. But then as time goes on, this wavelength is stretched. And well, that's because the universe has been expanding since between then and now. And Einstein had to abandon the static universe. Okay, galaxies on the average are moving apart. Our Milky Way itself, our galaxy is self-contained gravitationally, so it's not part of the Hubble expansion. But if you look on large enough scales, this picture is true. I think I'll skip the expanding universe, but okay, I'll do this one though. There's the Big Bang kind of gives people the wrong idea because it's not a point in space. So what is it? Well, if we take the universe now and we go backwards in time, it would be contracting, getting ever denser. Everything in this room would contract to a point, but it's possible the universe is infinite. In that case, no matter how much you squeeze things, contract, it's still infinite, okay? So the Big Bang is not a point in space, it's a point in time. And what is it that happens then? Is that the density becomes so high that our laws of physics, as we know them today, fail. You would need a theory of quantum gravity, quantum mechanics, together with gravity, and we just don't have it. People try string theory and so on and so forth, but that's what the hot Big Bang is. It's really when we have to give up. We don't know what to do. We don't know how to go farther back. And this term was originally coined by, I think it was by Hoyle. He didn't like the idea of the hot Big Bang at all. And so he made up that name because it was meant to ridicule the concept.
Hot mess.
But the name stuck. And anyway, there's no explosion and it's not a single point, but what the heck, let's put explosion everywhere. Okay, so where do we stand today? Well, as I was saying, major achievements in the last 100 years, but even more major achievements since the turn of the millennium. It's just amazing. We know the geometry of the universe. We know the total mass and energy content. We know the age of the universe. We know a lot of things, but the big one I'm talking about today, we don't know what it's made of. We don't know the dark matter and the dark energy. It's pretty weird. Well, let's talk about the geometry, the thing that we have learned. There were the three possible geometries. If you took Einstein's equations and applied them to the universe, you could have, these are the three, they're low dimensional analogs, of course, because that's the only thing we can draw. So we could be living on the surface of a sphere, or we could be living on a saddle, or if it's a flat geometry, that doesn't mean two-dimensional. It just means there's no curvature, no unusual mathematics. So for example, this is where the angles and triangles, this looks like a normal triangle, the angles add up to 180 degrees, normal stuff that we all learned. Now, if you go to the spherical geometry, then the triangle is, the angles would add up to more than 180, or the saddle, they would add up to less. So these guys have non-zero curvature as opposed to the flat geometry. And another slide just for fun. This is this little guy here. If you had, okay, the flat geometry, what we're used to, you send off two parallel light beams, they just go off parallel ad infinitum. But what if it's not? What if we're living on the surface of a saddle? There it is, and those light rays would diverge. Or if you're on the surface of a sphere, they would come back and bite you from behind. So those are the three possibilities. And the distinguishing between them happened around the turn of the millennium. It's kind of complicated, but I'm going to try to explain it at a the simplest level that it can. Let's look at the light left over from the Big Bang. This is light that was actually created 300,000 years after the Big Bang. It's the cosmic microwave background. But so photons from that time stream straight to us unimpeded. And everywhere you look in the universe, they're basically the same photons, but not quite, not quite. Some of those photons have a little more energy than the others. We talk about it in terms of a temperature, and the temperature difference means that you have hot spots shown in orange and blue spots shown in blue of this light. It's kind of when you take the Earth and you flatten it and make a picture of it. This is the universe. You flatten it and you make a picture of it. And the question is, how big are these? The hot spots are, by the way, the temperature difference from the average is 1 part in 10 to the 4. These were not easy measurements. This particular diagram, this is the best measurements that we have is from the Planck satellite. And then the question is, okay, look at one end of a hotspot and another, and those are moving towards our telescopes. But the question is, are those rays moving in a straight line or not? We know the distance to, we know how far away this thing is. We know that distance. We also know the distance across one of the hotspots from one end to the other. And so that should tell you what the angle is. So in our telescopes, it turns out if the universe has a flat geometry, then these hotspots should correspond in our telescope to 1 angular degree. Whereas if it's one of the other possibilities, then it would be more or less than 1 degree. Okay, so you take this data and you break it down into spherical harmonics, and boom, look at that, 1 angular degree. Geometry of the universe is flat. Now, the other peaks, there's 7 peaks in here in total, and the other peaks are really the best probe that we have of so many parameters of the universe. But again, I want to emphasize what flat geometry doesn't mean 2-dimensional. In fact, let's take a cube, take all the sides out to infinity in all different directions. So that would be the best analog. That's what I mean by flat geometry. Okay, so then the earlier satellite was the NASA's WMAP satellite. And this is just for fun. In here, you have the initials of Stephen Hawking. No. Oh, yeah. Yeah, see, isn't that fun? Yeah. Yeah, they're in the Planck data too, but it's just some cold regions that happen to look like those initials. Okay. Well, now let's turn to this question, what is the universe made of? And this is where it gets weird because everything that we're familiar with in our daily lives, the bodies, the air, the walls, the earth, the sun, all of that is made of atoms, as you know. But all of that adds up to only 5% of the content of the universe, which leaves us with a very weird conundrum. Here's what the universe looks like. 5% ordinary stuff, everything that we're used to. And the rest, 25% dark matter, more or less, and 70% dark energy, neither of which, I know this is the astronomical society, you probably like things that give off light. Well, this doesn't. That's what's meant by dark. And the question is, what is going on? But before I get there, I want to have a few more comments about the Big Bang, which is that it happened. We also know this from that data 14 billion years ago in a hot, dense soup, primordial soup of particles, which then, as time went on, spread out because the universe is cooling and expanding. So that's what Hubble discovered. All right, this is from my book, The Content of the Universe. You make a 10-ounce drink, and here are the pieces. Okay, really more like 2.5 ounces of dark matter. All right, so this problem of the existence of dark matter has now been around for 90 years with varying levels of certainty. Dates originally back to Knut Lundmark in Sweden and Fritz Zwicky, a Swiss scientist working again at the same observatories above Pasadena. And he in particular, that's Zwicky, and he in particular was looking at the Coma cluster, which has hundreds of galaxies in it. And he observed something surprising. If you watch one of these galaxies moving around the center, around the center of the cluster. And some of these are moving really, really fast. So the question is, why don't they just fly off? What is holding them in? The other galaxies are, that you know from how much light they give off, those things are not enough to hold in these, to sustain these rapid orbits. So the idea is to add an additional mass in the form of dunkle Materie, which is German for dark matter. But I do have to tell you a story about this guy. In his book, he called his colleagues spherical bastards because they're bastards no matter what direction you look at them from. I'm glad, wouldn't want him as a PhD advisor, but anyway. I have more stories. Shall I tell another story or shall I go on? Stories. Okay, so I was on this radio show on the West Coast, which on the East Coast amounted to 2 a.m. to 5 a.m. Okay, it's kind of, but I didn't make it through the whole thing. And it's for truckers. And a lot of them are quite educated scientifically. Some of the other ones are more interested in UFOs. Anyway, so the people call in with questions, and one woman called in, her name was Barbarella. So I said, hello, Barbarella. It was the daughter of Fritz Zwicky. And she was quite angry at the world because nobody had listened to him about dark matter, about its existence. She was going to write a book. I was flummoxed, and then eventually I said, well, nobody was listening then. Well, we're listening now. Okay, so apparently people did not listen enough, but then comes along Vera Rubin in the 1970s, and after her work, everybody was convinced. What she did was show that dark matter exists in every galaxy that you look at. So this becomes a problem that the scientific community really has to deal with. Here is an analog to what she did. Okay, she did not look at the solar system, but this is, so forget dark matter for the moment, but this is a perfect analog. And in the picture, I'm showing the average speeds of the planets. We start at the sun and we move to the right to farther and farther away from the sun. This is the radii of the orbits of the planets. And here's how fast they're moving. So the central one, Mercury, is the fastest. Then Venus and Earth, Mars, blah, blah, blah. And as you move farther out, the orbital speed gets lower.
Right.
And instead of removing Pluto as the 9th planet, I accidentally added 10. So I thought, okay, I guess I put in planet 9. Anyway, the equation describing this is Newton's laws. And so it turns out the speed, velocity v goes, well, as the radius of the orbit goes up, the velocity goes down. But as the mass interior to the orbit, like if the mass of the sun were twice or 4 times as much, the speed would be, of all of these guys, it would be twice as much. So it depends on how much mass is in there pulling on them. And I do have to tell stories about Tycho Brahe was a person who studied these planetary orbits. And he lost his nose in a duel. After that war, a gold and silver replacement. I'm not sure how that works. Then the story I'd always heard was that he died because he was at a dinner with the king, had too much wine, and you're not supposed to go to the bathroom until the king gets up. You're not supposed to get up till the king does. So he died 3 days later of a burst bladder. However, then there was a competing theory that it was mercury poisoning by his student Johannes Kepler. Those famous Kepler's laws really should have been Brahe's laws. They actually dug up his body about 20 years ago and tested all kinds of tests on his mustache hairs. No evidence of mercury poisoning. And okay, now I'm going to run out of time for the science because I'm telling you stories, but I'm going to do it anyway. So I'll tell you why I believe this story. I was as director of Nordita in Stockholm. I got to go to some of the Nobel ceremonies and the award ceremonies and the dinner and the parties and dancing and all that stuff. Now at the dinner, this is in the city hall, beautiful, very high ceilinged old building with the central table where the king, queen, and laureates sit. And by the way, the physics laureates are the closest to the king and queen. And then perpendicular to that central table are the tables of other guests, people who are coming to the dinner, including me. Well, I'm wearing my ball gown but I have to go to the bathroom, so I get up, I go around, all the way around, go to the bathroom, and on my way back, oh, I knew some people at the central table, I said hello. Well, I come back and the woman across from me, who's a member of the Nobel Committee, says, well, if you're going to get up to go to the ladies' room, then you should at least be discreet about it. I guess it's true, you're not supposed to get up until the king does. Well, I did not die of a first bladder.
You didn't drink enough wine.
I just didn't drink enough wine. Well, no, I went to the bathroom, that's the difference. Yeah, but it's probably both. Okay, well, that was the solar system analog for fun, and because it illustrates the point. Let's go back to galaxies, where you do the same thing. You start at the center of a galaxy and you watch something move around at some radius r away from the center. And same thing, the speed of the orbit is determined by the amount of mass interior to that orbit. More mass, the faster things go. Okay, so that's what she measured. Speeds of things moving around the center of galaxies. So here you start at the center of the galaxy and you move out the radial orbits as you move out of away from the center, and the speeds of the stars that she looked at. So now if this is what would have been expected, this is what the solar system looked like, right? Based on the stellar light, that's what you should have seen. Nope. Things are way up here. These are called flat rotation curves. These guys are moving way too fast. What the heck's going on? You have to add in more mass. So you add in this thing called the halo, add in more mass, and it works. That was the first evidence that dark matter has to be there. It has to support these rapid orbits. Otherwise, as I said, these things would just go flying off into space. Something is holding them in. All right, our Milky Way. I'll show some pictures of our Milky Way. Well, at the center, there is a supermassive black hole. It weighs about 4 million times as much as the sun. And these two shared the Nobel Prize for that discovery, the 2020 Nobel Prize. And the way they did it was same kind of thing, artist rendition here, but things move around the center, and from the velocities of stars in orbit, I'm having a little trouble with this. There we go, laser pointer. You watch things moving around, and their speeds are determined by the mass interior. Well, you watch something really close in, and there's too much mass interior unless it's a black hole. So that's how they were able to prove there's a black hole in there. I want to add right away, supermassive black holes are not the dark matter. There is one inside every galaxy in the center, but they add up to a tiny, tiny bit of the universe as a whole. All right, let's go back to the Milky Way. It's just shown in yellow, so you identify the black hole. Now there's these spiral arms. And this is when you look out at the sky and at the Milky Way, this is what you're seeing is all this stuff. The sun, for example, is out here. But you take all that and lay it on the side. That's the disk of the galaxy. It's a flat thing. Again, the sun is 25,000 light years away from the center. But that ain't nothing when it comes to the galaxy mass. This is artist rendition, of course, but there's the part of that we see of the Milky Way, but here's the whole thing. We know it's there. We know the mass is there. It's dark, it's not giving off light, and we don't know what it is. So this is what we're trying to figure out. Well, it was the rotation curves that first led people to the existence of dark matter, but at this point, there's a million pieces of evidence and nobody argues anymore. I'll show a few more. Einstein predicted from his relativity that mass bends light. So although whatever the dark matter is, this massive compact halo object, doesn't matter, whatever dark matter is, it doesn't give off light, but it bends light. You take some background star, here's your telescope, you're looking at a background star, and what happens is the mass bends the light. No kink. Sorry, that's the best I could do though. So, and then you'd say, well, this is what you'd see. You'd say, okay, the star's over there. Wait a minute, there's another image over there. Wait a minute. These images are very distorted looking, they're sheared. Why? Because they've been lensed. This gravitational lensing by this mass en route. So you can use images of distant stellar light to learn about the mass distribution of dark matter between those things and you. In fact, on your iPhone, a Michigan graduate student, Eli Reichhoff, wrote an app with the correct equations for gravitational lensing. You can lens yourself more. This is my student right here. More and more and more and more. But let's talk about actual data this is Hubble Space Telescope data. And these are distant objects that are getting lensed by stuff in front, and there's a lot of lensing going on. You see these multiple sheared images, and don't ask me the details. But from these kind of images, you can reconstruct what the dark matter was that made things look like that. And when you do that, you get images like the next one. But let me just tell you, the next image is a different lens system. But this is the mass, also Hubble Space Telescope data. This is the mass distribution that would produce such a lens system. And so this is actually a cluster with tons of galaxies. I think it's actually the same one Vicky was looking at, but I'm not 100% sure. But anyway, so in this mass, you've got the galaxies, but you've got more mass in between the galaxies. So there's even more dark matter. All right, rotation curves, lensing. Another one, this is the famous bullet cluster. They put this on posters all the time or talks about dark matter because it's such a beautiful image showing that ordinary matter and dark matter really do behave differently. What's going on here is two clusters they collided. And eventually they'll merge, but after that collision, what happened was that ordinary stuff, gas, it's shown in pink and it's identified because it gives off X-rays. The gas gets stuck. If you and I collide, we're getting stuck. There's electromagnetic interactions, there's strong interactions, which is what holds nuclei together, but the gas doesn't get very far. On the other hand, there's the second component of mass, also found by lensing, shown in blue, that just kept going. It didn't stop. So it doesn't have those interactions. It's these, so you can see clearly differentiation between ordinary stuff and dark matter. I'm gonna skip this, I think. And just review what I've been saying. I've been saying there's evidence for dark matter everywhere. And I've talked about a bunch of them, but I haven't even really, there's more. I didn't talk about all of it. And in particular, that picture I showed at the beginning, and I said you learn more from the 7 peaks. That is actually where we get our best unequivocal measurements of the amount of dark matter. And that's where you get this pie picture. Okay, so that's from the cosmic microwave background data. It's the best way to get those numbers. Well, okay, so it's there, but what is it? Well, it's not, people tried it right away, things like rocks and dust and snowballs, and no, it's not, because they'd have observational consequences that are wrong. And where do we stand now? Well, we have a lot of possibilities. We have candidates that people are working on all kinds of things. The top two are the best ones from the point of view of theoretical motivation, so I'll return to those. But before I do, neutrinos, they exist. That would have been really nice if they solved the dark matter problem, but they don't. They're too light. They would screw up galaxy formation. And that was known in the 80s. And since then, multiple Nobel Prizes have gone to mass measurements. They're about 0.5% of the content of the universe. I need some water. Luckily, I have some. I did. Did I leave it lying around? Oh, shoot. Did I leave water back there somewhere, you guys? Thank you, Roger. Thank you. I had a full bottle back there. Is that my bottle?
Yes, ma'am.
All right, why don't I don't need to open another one then. Thank you. Thank you both. I've been having trouble with allergies. And miserable. Yeah, it's making my throat close in. Anyway, so, all right, so neutrinos are only 0.5% of the universe, and they just don't behave correctly at all. But there are a lot of other candidates. These would be additional neutrinos and on top of the standard ones. They're interesting, sterile neutrinos. I want to say a few words about primordial black holes. I'm showing pictures of my group members who have sort of become leaders in some of these, in these areas. And primordial black holes, what are they? They're little black holes that form very early in the history of the universe. Whenever you have some patch of the universe that has a lot of matter in it, so much matter that it's, instead of being part of the Hubble expansion, it just collapses in and of itself to make little black holes. This happens when there are phase transitions in the early universe, like boiling water, the other way around, because the universe is cooling. And that's an example of how these might form. This idea has been around for a long time, but it's gotten this resurgence of interest because of LIGO. So in 2016, LIGO discovered gravitational waves. This is the LIGO detector. Einstein predicted anytime mass moves, it should make gravitational waves, but these are tiny what I'm making here. But if you have merging black holes, then it gets interesting. Those have been detected. And the way it works, it's unbelievable. So gravitational waves stretch space in one direction, squeeze it in the other, and then it goes the other way around. So they're going like, make space do this. And these are 4-kilometer long arms in perpendicular directions. So one of them is bigger by the fraction of a proton mass. One of them gets smaller when a gravitational wave goes by, and they measured it. And they're learning all about, yeah, you should get somebody here from physics to tell you about this subject. It's really amazing. And so there, you can tell all kinds of learning, all kinds of stuff about black holes. The original ones were about 30 times the mass of the sun and great primordial black hole possibilities. So that's why people got excited. Let me turn now to the two candidates that I said are the best motivated, and those are the WIMPs and the axions. Why are they the best motivated? Well, because particle theory is an incomplete business. There are unsolved problems, and in the course of trying to solve those problems, you automatically produce dark matter candidates that they're not invented to explain dark matter. They're there anyhow in the theory. I won't say much about axions. They're very, very light particles. I mentioned the theory of strong interactions that holds your nuclei together. Well, there's some problems in that theory, but when you solve those problems, you automatically get axions simultaneously proposed by our favorite Steve Weinberg and also Frank Wilczek, another Nobel laureate. And I have to say a few words now about Steve Weinberg. I think people here know him, but his office was 3 doors down from mine, and he was one of the founders of the standard model of particle physics, explaining all that atomic stuff, and one of the great minds of our time, also communicating incredibly beautifully to the public with his books and articles. And yeah, a loss for us that he passed away 2.5 years ago. In his honor, we now have the Weinberg Institute for Theoretical Physics. So I thought this is something that you'd want to know about. I'm the director of the Institute, and within the Institute, there are 3 centers. There's the cosmology and how do you pronounce it? Astroparticle. So TCAP, and then there's the Center for Gravitational Physics, and then there's the Particle Theory Center. And we've had a Weinberg Memorial Lecture every other year. The first one was Frank Wilczek. And it was in April of last year, a year ago, we had Jim Peebles, one of the founders of cosmology. So keep an eye out for those talks, okay? We also had in November, the Weinberg Inaugural Conference, some amazing speakers. So anyhow, you guys should be on the mailing list for these, for our events, because I think you find some of them, especially the every other year public lectures. The next one, so we had particle physics, we had cosmology, the next one will be relativity. So you might be interested.
Yeah, check into it.
Yeah, I think that was
I was there for the Dr. People's lecture.
wasn't that amazing?
It was.
It's just amazing. The People's Lecture was just amazing.
Yes.
It is online if you want to look at these talks, but I don't know, the recordings were not done that well, if you ask me, but there's nothing I could do about that. So.
The passion the man showed was incredible.
Sorry, the what?
The passion he showed was incredible.
Oh my God, yeah. So by the way, he's 91, or I guess now he's 92. And he said, he told me he doesn't want to travel and I talked him into it. I'm really proud of myself that I got him
Now,
here.
who is this again? I missed that.
James Peebles,
Peebles, okay. You
Nobel
mentioned-
laureate in, I don't know, 2022 or something,
Okay, yeah.
but an amazing guy.
Okay.
You can, so yeah, if you're, if you want me to send you the link, I can do that.
Yeah.
Actually, go to the Weinberg Institute for Theoretical Physics webpage. You don't know how much I've struggled over all of this stuff. So that's my webpage. I made it, basically, the content. And you can find all this in there, okay? If you want to take a look at some of the events that happened. Okay, great. Well, axions, what's happening now is the theory was great, and now the thing that's interesting is experiments are really looking for it. And again, one of my group members put together this review about all the different experiments looking for it. It's kind of amazing. And then the one I want to talk about, and I'm not going to show every slide I have here, I promise, because of how many? Oh, yeah,
15.
plenty. Anyway, but I want to tell you what it is. So these are WIMPs, and what does that name mean? Well, the WI means weakly interacting. I mentioned that they don't have strong or electromagnetic interactions, the dark matter particles. They do feel gravity, so they do clump together. But okay, we know of 4 fundamental forces in nature. I make all my students, I put it on every midterm, every final for the for the less scientific folks. I make them learn it. So the 4th force is the weak force, which is responsible for some types of radioactivity. And so that's what weakly interacting means, that they feel gravity and the weak force. And they weigh about 1 to 10,000 times as much as protons. So that's what the massive part of the name is. Okay, so we're gonna make a postulate. The dark matter interacts with the weak force. What is the consequence? Forget the equation, but the consequence is if you make that assumption, you get the right amount of dark matter today. That's huge. We go back in the early universe and we watch particles interact with each other. We know how many there are and what they're doing. These guys are their own antimatter. So when 2 of them hit each other, they annihilate, which means simply that they turn into something else. And so you watch this annihilation process, but then eventually the universe becomes too spread out. The annihilation stops. They don't see each other anymore. How many are left? The right amount to make the dark matter. The only ingredient being the weak force to get that annihilation, to figure out how much annihilation is going on. That's what they use to annihilate. That some people call this the WIMP miracle. I don't know the coincidence. I don't know. Anyway, that got people pretty excited. Then the second reason people are excited is because I mentioned that you kill 2 birds with 1 stone. If you have, for example, if in particle theory, there are extensions of the standard model, such as supersymmetry, which means every particle we know about would have a companion. They're heavy, which is why we don't see them all the time. The heaviest one decays to the next heaviest, blah, 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 until you get to the lightest one, and the lightest one would be the WIMP candidate. So these are 2 reasons why on theoretical grounds, WIMPs are great. Question is, well, how do we check? We gotta find them. We gotta detect them. There's a 3-pronged approach. You make them, shake them, or break them. And then I may run out of time before I can tell you about my 4th. This is my baby dark stars. Let's talk about making them. This happens at CERN, the particle accelerator. The Large Hadron Collider accelerates, it's a 17-mile ring. And there's Lake Geneva, and there's, you can ski. And there are protons accelerated in opposing directions, smashed into each other, and there are detectors at those collision points. The 2 detectors were really that are used for this kind of work is the Atlas detector, and I'm just showing here Fabiola Gianotti. She was the head of CERN until a few weeks ago. And this is the Atlas detector. I don't know if many of you may have seen such pictures where this is a person just showing how mammoth these things are. And then the other one that is used as a CMS detector with Peter Higgs in front. One of the people who proposed the Higgs boson. the final missing piece of the standard model. And sure enough, the Large Hadron Collider did discover the Higgs boson. There's this bump here at 125 times the proton mass. I'm not getting this thing. Uh-oh. Have I killed this thing already? Battery's dead.
Nope.
No, there it is.
You're right.
There it is. Okay, 125 times the mass of a proton, the Higgs boson. The second major goal of the LHC was to search for supersymmetry in dark matter, and no discovery yet. Which is sort of disappointing, but that's the way it is. Could be, you might have to go to higher energies, build another machine, see how long that takes. So the protons collide and then produce some supersymmetric particles, and which decay in a chain until you get to the lightest one. And definitely this battery's on the way out. So, but the lightest one then escapes. So you have missing energy, and from these chains along the way, you also have information. So this is how you would look for these particles, and there's been no detection yet. Which means things are being pushed to higher masses. All right, that was Make It. There's also, this one is Shake It. Okay. This is, well, oh, I forgot to mention, I had it on the slide, I forgot to say, a reporter asked me, all right, how often would one of these particles hit your body?
Oh, yeah.
Okay, and there's billions going through you per second. We ended up writing a paper on it. And about one, depending on the details, somewhere around one every few weeks would hit one of your nuclei, and you're still here, right? So why? Because the weak force is called the weak force for a reason. It doesn't do much. What that means is the experiments are really hard. You're looking for something that interacts weakly. All right, so let's take these WIMPs that are flying around here anyway, stick a detector in the way, and the WIMP will then scatter off of a nucleus, and in the process, deposit a little bit of energy in the nucleus. And there's many ways that you could then try to figure out that happened. But unfortunately, the count rates are very low, less than one count per kilogram of detector per day. So now then I'm going to then now I'm going to turn, people ask, how did I get into this business? And I will show you who got me into it. And that's my PhD advisor at the University of Chicago, David Schramm. He was a force of nature. He was one of the founders of the field of astroparticle physics. And he was also, you can't tell how big he is in this picture, but he was a big guy. He was an Olympic Greco-Roman wrestler, Olympic hopeful, didn't make it to the Olympics. And when he was his legs were like this, when you skied with him, there was a mogul and he went ahead of you. Well, by the time he got through it, there was no more mogul. Yeah. Now, unfortunately, he died flying his own plane from Denver to Aspen, and when he was 52. But yeah, we remember him very fondly. And by the way, his nickname was Schrambo. So my beloved advisor. All right, so that's me in grad school, and then I took a postdoc at the Harvard Center for Astrophysics and went to a conference in Jerusalem where I met this guy, André Druckier. He's Polish, but he speaks English, French, German, Polish all at the same time. But anyway, so he came up, he'd been doing some really interesting work, and he came and visited us at Harvard, and over there's David Spergel, who's now the director of the Simons Foundation. And we wrote some papers about this picture I showed you, okay? So I calculated the particle physics, and David did the astrophysics, and the question was, well, what do you get when you do those calculations? And what we found was that this is something, what the count rates and experiments would be very reasonable, and people started building. That was a long time ago, 1986. But what kind of stuff are they building? Well, here's an example. First of all, you have to go a mile underground to get away from cosmic rays, because those are the particles in the galaxy that have electromagnetic interactions, and they are dangerous for us. And yes, they dominate, but they can't get through the Earth. They can't get to these detectors because they have much stronger interactions. So in the Gran Sasso Tunnel, I was just there last summer. It's really cool. You drive up this mountain, and there's this tunnel that goes underneath the mountain peak, and inside that tunnel, that's where all these experiments are. It's very cool. And including the xenon experiment, which is tons and tons of xenon that are sitting there waiting for dark matter to hit. In fact, this is a worldwide effort. These are the different experiments all over the world. The one that has been exciting is in the same Grand National Tunnel. There's also the Dama experiment, Italian experiment. It's the only one that's been claiming detection. And what's exciting for me is they used our idea to claim detection, which is the fact that the Earth goes around the sun, like in that picture, means that the count rate changes with the time of year. It goes up and down. I can see, okay, that's what we predicted with a peak in June and minimum in December. And that's exactly what they have. And they've got statistically 14 sigma, doesn't matter. I mean, it's incredibly statistically significant. They are seeing annual modulation, but the question is it from dark matter or not? And they've been looking at this thing for, I don't know, 15 years, no more than that. They have tons of data, but they won't release their data to the public, which is unusual. And then other experiments have not confirmed their results, but it's not clear, it hasn't been clear how to compare because others, like xenon is made of xenon. Dama is made of sodium iodide crystals. So how the hell do you compare? Because there's different, the interactions can be a little different. The nuclear physics can be different. Got to show this picture. She's the leader of the Dama, PI of the Dama experiment. She's the PI of the xenon experiment. And Juan Colbert, our different experiment, says, I'm a Spaniard caught between two Italian women. So we have fun. So anyhow, if you make some very simplistic assumptions, then Dama in green would be ruled out because you're supposed to be below the red curves. But that assumes you know the details of the interaction, which you don't. So this assumes too much. However, now there's been excitement because finally other groups are using the same material, these sodium iodide crystals. And there is one in particular, the cosine 100 is in Korea, that does not see modulation. And so Dama's not quite ruled out yet, but it looks like that's where it's headed. Oh, damn. Yeah. Okay, so I've had some ideas for other approaches for dark matter detectors, including DNA attached to gold. That's a cool idea. But I'm going to tell you a little more about this one because it's happening. The paleo detectors. This is the idea that, okay, instead of using tons and tons of xenon, let's use little rocks from deep underground that they're ancient minerals that have been collecting tracks for 500 million years. You're replacing the size with time. We're talking a lot cheaper to do this. New ideas, and then these guys, especially Pat Stengel, really led the effort. We wrote, you can write a bunch of theory papers, that's nice. But he actually got people collected together to start doing this. So the first meeting on this, I was like, what happened? People from Japan, people from the Karlsruhe Institute of Technology in Germany, people from everywhere. And that Trieste, I'm really glad I went to that meeting because I learned about Aperol Spritz. Anyway, it's just, by the way, from Trieste, Aperol. I guess you guys don't know what I'm talking about.
A drink.
Yeah, it's a drink. Yeah, right. Go try Aperol Spritz. Not in the US, it's not for you. Anyway, and so what the latest of this is the National Science Foundation has now given 2.5 million to, it's actually led by a guy at Virginia Tech. And we're talking, these tracks, by the way, are nanometer long. So the readout on that is new, couldn't have been done until pretty recently. And their approach is called color centers. But it's an NSF proposal. I'm on it as well for 2.5 million for lots of people. And then I used to be at Michigan before coming here. So a guy in Michigan also is doing stuff now, Charles Spitz, and he's got 1.5 million from the Moore Foundation. So this is actually happening. You can do a lot more with it, even if you don't find dark matter. You can also study neutrinos, the history of supernovae in our galaxy over time, getting rocks at different ages. You can also use it for reactor monitoring. So, nuclear non-proliferation stuff, which is what the Virginia Tech guys were actually using color centers for. So you can do a lot of different things. Atmospheric neutrinos, solar neutrinos, you study a lot. Cool new concept. Yep. here we are having fun. I went to this meeting a few weeks ago. It's an older picture, but same people. Then there's also, I don't want to go on forever, so I may not.
That's all right. You keep
got it
going
for
for
now,
a while,
baby.
yeah.
Oh, all right, all right.
As long as you're out of here by Monday morning, you know.
This one before the stock market opens. That was not funny. So, third way would be, let's see, we had make it, shake it, break it. All right, so annihilation still does happen, not in the average universe, but if you have pockets that have extra dark matter, which is true at the center of our galaxy or any other galaxy, is a lot more dark matter than average at the centers of things. They're pulled in gravitation. Okay, so what annihilation means is you start with two dark matter particles and they hit each other and turn into other stuff. And they go through a chain of stuff, the standard model, standard particles. At the end, you get the things in purple. You would get neutrinos, positrons, that's the antimatter for electrons, and gamma rays are high energy photons, high energy particles of light.
So they're not really weakly interacting with themselves.
They are. Yes.
They are, okay.
Yes.
Well,
Exactly right.
annihilation sounds like a pretty strong interaction.
Well, what the weak force does, it means that between two particles, you're exchanging a W or Z boson. So you have two of these WIMPs and this, and they come together and turn into, and then you have this virtual particle, virtual W's and Z's, and then they turn into something else. So yes, it's with weak force, absolutely. Mhm.
Super quickly, just to confirm, gravity is doing nothing at the scale, yes?
Gravity is, well, it has to, it's the reason why you'd have a lot of dark matter in the same location, but that's it. It has nothing to do with the annihilation now. They have to be able to find each other, so you have to pile them up. So gravity helps with that. But that's it. Okay, now people are looking for these three end products. Well, this one, the one on the right is fun. That's Ice Cube, which is looking for neutrinos. These are at the South Pole. You go down 2 kilometers and you've got these phototubes that go, this is an incredible technology to put those in there. You have to, you know how you drill? With hot water. Blast hot water down there and you have to hurry up and get the stuff down there before it freezes up again. It's quite an amazing technology. There's the Eiffel Tower for comparison. They have done amazing neutrino studies, found the highest energy neutrinos ever and high energy particles that people don't know how to explain, but nothing from dark matter yet. And then this is aboard the International Space Station, the AMS. And it has found an excess of positrons, but it's not dark matter. They thought they did. So you keep getting these, wishful hints and then they go away. The Fermi also has a hint, okay, and this one's still sticking around, and that is the Fermi satellite is looking for these high energy photons, gamma rays, as a satellite, and they see the gamma ray sky. Before I showed you the microwave background,
Right.
that was microwave sky. This is a gamma ray sky, different wavelength. And so there's our universe, and there are these double bubbles. My friend found those, kind of cool. But the only thing that's relevant for dark matter is smack. Oh, I can use the pointer on my mouse on the computer. Oh, yeah, good idea. Okay, so there, smack in the middle, there's an excess gamma ray signal. And the question is, what is it? Could it be from dark matter annihilation? And there's huge arguments about that. And it's not, we don't know, but interesting for sure. Okay, so I do get to talk about dark stars. Yes. Well, we proposed them in 2007, we being Doug Spoliar, Paulo Gondolo, and me. And, well, we didn't know about this cult film. But it's, you know what, I watched it, it's terrible, but it's a cult film, so maybe you'll like it. I don't know. Anyway, so what are dark stars? Well, I want to emphasize right away that these are stars made almost entirely of hydrogen and helium from the Big Bang. Okay, they're made of they're not made of dark matter. People from the name get the wrong idea. They're made of ordinary matter, hydrogen and helium, but the power source is dark matter. Okay, well, there is dark matter in there, but it constitutes less than 0.1% of the mass of the star. It's not fusion, Dark matter annihilation is the power source.
Hmm.
And this can go on for a long time and they can grow to be very large.
10
They grow
million
to be up to
souls.
10 million times the mass of the sun, biggest stars ever, and 10 billion times as bright. Two consequences of having big things like that. We have candidates in the James Webb Space Telescope, very exciting for us. And you can explain supermassive black holes. And instead of doing everything on one slide, I'm going to back up and do a few slides now on the whole thing. Let me back up. We're talking, these are the first stars to form in the history of the universe when it was 200 million years old. Where do they form? They form inside, I'll call them protogalaxies, little things. The Milky Way is a million times as massive as the little things that were existed back then, which then merged together, eventually making the galaxies. And inside these mini halos, smack in the middle, as I said, you have a lot of dark matter. That's where the star formation first begins. You have clouds of hydrogen that begin to collapse. It's the first time that you've got anything doing anything like that that's happening. Clouds of collapsing hydrogen. In the standard picture, they would make very tiny. They would collapse until they get to 10 to the minus 3 times the mass of the sun, and then grow back up to maybe 100 times the mass of the sun with fusion in them. But we're talking, so we asked, wait a minute, but there's a lot of dark matter. Doesn't that do something? The answer is yes. As that cloud collapses, the dark matter, it pulls in more dark matter. You get dark matter annihilation going big time. Dark matter annihilation produces, as I showed you, gamma rays, electron positron pairs, and they collide with the hydrogen in the cloud, and so they get stuck. So what that means is it's like you're dumping heat into the cloud. You're taking the energy that was in the mass of the dark matter, and you're dumping it into the cloud. As a consequence, that cloud can no longer collapse. That's what we did at first. It took another year to realize, oh, it's actually a star. It's not just a stalled cloud. This thing can satisfy all the equations, four equations of stellar structure. You can satisfy all of them. It's a normal star in that sense, but a weird looking one. But it is it's a real star, which also means it's not dark. It's giving off light. Right. So we got that wrong. We didn't know that when we called it dark stars. But anyway, and all right. So so a dark star is born, and when it's born, it's about the same mass as the sun, but it's very weird. Let me tell you what I mean. Well, the radii are enormous. It's 10 AU, 10 times the distance between the Earth and the sun. That's how big they are. So they're gigantic in radius. And there's no fusion in there. They're very cool. Okay, no, in order for fusion, you have to need a hot core to get fusion going. To have hydrogen burning to helium, you need a very hot central core. We don't have that. We have dark matter everywhere, and the dark matter power is spread out equally throughout the damn thing. And because it's so cool, there's nothing coming off to prevent accretion. So they can grow, and which is why they can grow to be so big. As I said, 1 million or 10 million times the mass of the sun.
Are they in hydrostatic equilibrium?
Yes. They're in hydrostatic equilibrium, they're in thermal equilibrium, yes.
But it's different parameters from a normal star.
Yes, like R, the radius.
Yeah.
Right, is different, yes, different parameters, but satisfying, you know, that in the standard, well, I'll show you a picture in a second, but the surface temperature is 10,000 Kelvin, which is about sort of like the sun, much cooler than other things people were talking about in the early universe. All right, so for those of you who are familiar with the Hertzsprung-Russell diagram, that sounds like that might be you. Anyway, so here they are. Let's stick to the right-hand side. Those are the ones I've been talking about over here. Yeah. Well, we grow them. All right, so the way we do it, let's say you have one. You start with one solar mass, you add on another solar mass, and each time you vary the radius until you're in hydrostatic and thermal equilibrium. Then you put on another solar mass, make sure you're in equilibrium, etc., etc. Just keep growing the damn thing. So we let her rip, okay? And here you go, depending on the mass of the WIMP, because they're a little different, but not very. let's look at this red thing. So they grow to 100 solar masses. Let's see, 100 is here, then 1,000, then 10 to the 4, 10 to the 5. This picture just cuts it off, but and when you get here, then you find this is how bright the stars are. This is their surface temperature. And normally that's when this kind of diagram where you see the main sequence, all the normal stars and the red giants and horizontal branch, all that stuff. It's the same diagram, but we're in a different part of it. And when we got up here, we realized this is from numerical results. Luminosity, the brightness deals with the mass. Well, guess what? Fred, who was it that found that? Willie Fowler, I think, Fowler and Hoyle found luminosity proportional to mass for supermassive stars like this. They found that in the 1950s, but they didn't have a power source for it. So we got it right. Funny, isn't it? A very simple argument for why it should follow that. We just found it numerically. All right. Well, what happens next if these things, eventually you'll leave your dark matter rich environment. You go somewhere, and then what happens? Well, stars are known to have gravity versus pressure, right? Pressure keeps them a lot out, and gravity pulls in. You remove the heat source, and boom, collapses to black holes. If you have million solar mass black holes very, very early in the universe, that's a great thing to explain the many giant supermassive black holes. The JWST is finding one after another, these huge things very early on that are really hard to figure out where do they come from. So if we give them seeds of 1 million solar masses, then you can make them. If you started with 100 solar mass seeds, forget it. So that helps with the big black hole problem. That's fun. The other thing about being big, observable with the James Webb Space Telescope. In fact, we have candidates. One supermassive dark star would be as bright as an entire early galaxy of stars. In 2010, John Mather, the Nobel laureate who is responsible for the JWST, came up to us and said, "Come on, tell us what these things are going to look like." So I had a student figure that out. We have a very simple-minded diagram that I think shows the point, though. This is how bright they are in different filters, different wavelength bands of JWST in blue. And yes, these things stick out. So yes, you can see them. We did a better job than this, but anyway, so the answer is yes, you can see them. And what we have now is yes, we have candidates, which is pretty cool. So let's see, these are the, in JWST, there's a field that they looked at, and they had 4 candidates, 4 objects where they had the spectra, which is what you need to prove that how far away they are. So this was redshift 11, redshift 13. Those are good candidates. And we've got more now. I just want to show you spectra. In the black dots are the data, and the blue dots are spectra for one of the dark stars. And here are the filters. So these are definitely sticking out above the JWST. You're seeing these. And this cutoff is because you've got hydrogen between these distant objects and you, and the hydrogen swallows all the light. It's called, so Lyman alpha absorption. So where that cutoff is tells you how far away the object is actually. So so now there's a weird situation with JWSTs. They're seeing too many and too massive early objects. If they're all galaxies, then that's a problem for the standard model of cosmology, the lambda CDM model of cosmology. So this is people are trying to figure out what's going on. Well, that's because some of them could be dark stars and not galaxies, and then we'd solve the problem. Is this wishful thinking? I don't know. Anyway, so we have candidates, so that's exciting.
So how will they be verified?
The ones that exist, the ones I'm talking about here already, those things have already been looked at like for a month. What we need, probably future objects. Now, in the future, you will have objects that are lensed. Same thing I've been talking about. The lens means magnified. And they've already got highly magnified objects by a factor of 100 or whatever. So if you get one that's lensed, you'll have really good spectra, because the spectra aren't good enough right now. If you find carbon and nitrogen lines, it's not a dark star. It has to be hydrogen, helium only. And we are predicting a helium-2 absorption line, the particular absorption line that only would be from the dark stars. So if you see that, that's really good great for us. Well, I'm gonna end with a joke. The thing that's really weird, of course, is the 70% dark energy. What the heck is that? And the only thing that we do know is matter, whether it's regular or dark matter, is gravitationally attractive. That's the definition of matter.
Right.
This stuff, on the other hand, is causing acceleration, so it is in some sense repulsive, and we don't know anything about it, really. The same picture I had before, well, there are galaxies accelerating apart, and why, we don't know. So here comes the joke. There I was at the World Science Festival in New York, and the three of us were talking about dark matter. And the three of them were talking about dark energy. And as I told you, we only know one thing about the difference. Dark matter, dark energy.
Yeah.
I had that planned before we got on this panel. Okay, so I think I hope I haven't gone too long. I went an hour.
Fine, it's great.
Well, I went for an hour, but I would have stopped if I started thinking you guys were fading.
You're
You
fine.
didn't.
Very interesting. Questions?
Oh, yeah, and here's my summary again.
Maybe a little bit, I'm not a physicist, but
David, I'm probably gonna go.
if Einstein's equation E equals MC squared is correct, the energy should have gravitational effect just as much as mass, shouldn't it?
Yeah, so where's this picture again? In the ordinary world, energy and mass are related, right? But the dark matter and the dark energy have nothing to do with each other, except that they're both dark. So it's a terrible names.
So the names are misleading to call them.
The name dark energy is misleading as hell, yeah.
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 Oh, no, scientists name something probably
Well, dark matter is a good name, but dark energy is not. My friend Michael Turner came up with the name and I couldn't believe it stuck.
So if these dark stars have this much hydrogen and helium around them, that's what's causing them to give off light. What's stopping that hydrogen and helium from fusing,
Oh, it's
Because
because
it's not heat.
it's not hot enough.
Yeah.
Hydrogen burning helium requires 10⁻⁷ Kelvin. We don't have that. That's why the core of the sun is hot. The core of these things there is no core.
Yeah.
So wait, so there's a question there?
Can you speak a little bit about modified gravity or MOND and
Sure.
why it fell out of favor?
Yeah. So the rotation curve stuff I started out with immediately had another potential solution. This guy Milgram proposed modified Newtonian dynamics, or MOND. The idea is that Newton's laws change when you get out to the edge of the galaxy. It's not F equals ma. So when you get to low acceleration out there, the laws are different. And of course, you can write down a model that does that. And then that was, people thought that was interesting, but it's just something that fits the data. Then along comes Bekenstein, who also did some famous work on black holes, coming up with not just a phenomenological model, there's not just something, but an actual mathematically consistent starting point that would give you those results. Which it morphed eventually into something called TEVIS, tensor vector scalar. And nowadays, in order for it to work, you have to have dark matter in addition to all these new particles. So it's pretty unsatisfying at this point. Especially the cosmic microwave background data is very hard to explain without dark matter. People, they all agree. The thing is on the rotation, on the length scales of rotation curves, it still works really well. So there's this really fascinating. However, on large scales, it doesn't work.
You mentioned like old black holes or small black holes.
Primordial black holes.
Right, we don't really know what happens when a black hole reaches the event horizon, so could some of these like really old and small ones just belched out stuff that they changed while all of the stuff was falling into them?
I'm not sure what you're saying, but I will say that black holes do evaporate by Hawking evaporation. So if they're smaller than 10 to the 15 kilograms, they wouldn't have lasted long enough to still be here today because they would have evaporated away.
Well, I mean, what happens to the stuff that they?
The stuff that goes in,
Yeah.
that's what everybody wants to know.
The source of. Goes in but doesn't come out the same way, so we don't see it anymore.
Well, that's called a black hole. Yeah, the primordial black hole. Yeah, that's a possibility. Yep. Sorry, you've had your hand up for a while.
So if James Webb Space Telescope could potentially detect these dark stars, is there a possibility that we could also be utilizing it to detect exoplanets around these dark stars?
Oh, hell yes. No, not around the dark stars,
Not
but it is looking for exoplanets.
Well,
One of the
no,
other main
Yeah.
things it's doing.
Yeah.
Yes.
Is it just that they're not bright enough?
You mean why they're not around dark stars?
No. I mean, would a dark star have a planet shape?
Why would you have planet formation around a dark star?
No, I don't think you would. No. I never thought about it, but I don't think so.
I mean, if it's just hydrogen and helium, there's nothing to form.
Right.
Well, unless how we are observing dark stars now is just one stage of its.
That's true.
Well, we don't think they exist anymore today. These are the first stars. But the JWST is definitely looking for exoplanets.
Finding exoplanets.
Finding exoplanets, yes.
Good.
Oh.
Yeah, I was gonna ask you for your comments on the observations of the James Webb Telescope that suggest some of the earliest galaxies are further along their evolutionary path than what might have been expected. And I know there's even some papers suggesting that maybe the universe is actually older than it is and it's missing dark.
Oh, that I think is a bunch of nonsense.
That's what I thought. I've asked many people, I got the same answer, but as to the galaxies further along their evolutionary path, is that?
Yeah, that could
maybe
be,
bad
So that
data?
ties into this question about are there, like, one galaxy already, the amount of stellar light they're seeing in there you'd have to recycle all the baryons. It just doesn't make sense, all right? So that is already a problem. But then there are those, look, I don't even know. Ironically, Mike Bolincoach in astronomy is the guy who first pointed that out. And I was talking to him today about something else. And I forgot to ask him what the current status is. So I'm really annoyed because we're doing some work that's related to this question and I need to get his take on it. So I'm not sure what's going on with that, but that's tied into this question of, well, okay, so the star formation rate and and all these things. Yes, it's a very interesting subject and it's not resolved.
But it could just simply be maybe the way the data is interpreted or the models that you
Yes.
interpret the data. Could
But
just
this has
simply
nothing
be
to,
wrong.
what I'm talking about now has nothing to do with dark stars, but
Right,
but a theory goes into it, yes. Yeah, this for sure. And so that's in the IMF, the initial mass function stars, how many objects with of what mass and and so there's maybe, so if there's some of the theories off, then the estimate of the mass is off, et cetera, and the star formation rate and all of this stuff is complicated. Wait a minute, did you get your question?
No, I did not. If the excuse me, if the dark matter estimate is correct at about a quarter of what's in the universe.
We think, yes, we believe
Yeah.
in dark matter.
Yes. Is it all going to be found in dark stars? And if so,
No,
shouldn't we
no,
find
no,
them
no,
all
no,
over the
no,
place?
no, dark stars would be a
Just a
tiny
small-
part of the universe.
Oh, right, but a tiny part of where the dark matter is?
No, I'm just saying that there aren't that many dark stars, so the dark
Okay.
matter is all over the place, and there's a couple of dark stars here and there.
Oh, okay, so what other things you think is just lying around?
Well, the dark matter is just flying around,
They're
yeah,
just lying, okay.
yeah, individual particles,
Mhm.
if it's a particle, which is what we think, but who
Mhm.
knows? But you know what, there was a question back there, and then your question, and then I'm done. Okay, awesome.
How stable do you think our current understanding of the flat universe is?
Oh, it is. We're done.
I remember a UT astronomer, it's been a couple of decades ago, I can't remember who it was. He came and talked to us and he handed out, he had a can of Pringles and he handed Pringles and everybody take one and that was the shape of the universe. They
Saddle,
understood
the
it.
saddle.
It was the saddle.
Oh, that was
right?
just wrong.
But 10
Enjoy your
years, 20
Pringles.
years,
No, the The data that I've showed you, like the Planck satellite
Yeah,
data, that's it. That's the best you're ever gonna get on those temperature, on the anisotropy of the temperature. It's that good. It's not gonna
Okay.
change. Nope, that's not changing anymore.
all right.
No, I wonder who that was that told you. That's interesting.
Yeah, I'd have to look back.
20 years ago or 40 years ago?
Oh, no, it's decades ago.
Because these discoveries were around, early 2000s.
Yeah.
Before that, we
Well,
had,
that would be.
so the saddle would have been less than, mega less than 1, yeah. Well, if you only know about the ordinary matter, that's what you would get, yeah.
I mean, the Hubble.
Or even all matter adds up to less than. In order to get this flat geometry, you need all pieces of this pie. If you only had the matter pieces, you'd have less total stuff, and that would be a saddle. So this, right? So
Yes,
anyway, so all of this stuff, this picture is new. It's all post 2000. New in that.
Are those ratios constant over time or are they varying?
What?
The ratios, are they constant?
Varying over time for sure.
Yeah.
Early in the universe, the dark energy was completely uninteresting and negligible, and it just became important recently. What the dot. It's called the coincidence problem. Right around the time we come to exist, all of a sudden
Yeah.
dark energy shows up.
Mm.
Right? It's pretty weird. Really, really unexplained, this dark energy business. All right, I'll tell you, I have a model that I call Cardassian cosmology. It doesn't have dark energy. You change the equations instead, the evolution equations for the universe. You only have ordinary and dark matter, no dark energy, so it's possible. But this is, I'm showing you standard law. The dark matter is there, dark energy.
Yeah, right.
Yeah, I just was, I'm fascinated with the halo, the dark matter halos around galaxies. So they're kind of accumulating around the galaxies, or they.
Oh, no, it's the other way around. They were
They-
there from they were first.
And they started the accretion of actual matter to make the galaxy.
Yes,
Something
they
like
were
that.
there first, and then the ordinary matter fell in. And it has all these interactions that make it flatten out into the disk.
So it seems like it's almost, there's proof of dark matter in the way that it behaves around in the galaxy halos. Or around the galaxy.
Yeah, Jerry Ostrager just died, and Ostrager and Peoples pointed out that you need it without a sphere around it, the halo, the rest of the Milky Way wouldn't be stable.
Okay. Awesome.
Yeah.
Kind of a container.
Well, I guess we can wrap it up, but I didn't see any questions online.
Oh,
It-
I'm
it-
sorry, I
it-
forgot to even take a look.
Checked.
Another question, which may not be completely related to this, but
I said after her, I'm done. I'm gonna run out of steam.
If the dark energy keeps increasing and the dark energy is with.
Okay, so
driving
now
this-
there's new data that I didn't talk about, tentative from the experiment called, the telescope called DESI. If DESI's results are correct, the dark energy is now going back down in importance.
Well,
In the future, it'll go away.
presumption was that if it
Yeah.
were growing, that the universe would just explode into infinite size, all the atoms would rip apart and.
That's
everything.
possible, if dark energy was strong enough, that's true.
Yeah.
Yep. That's
But-
called the big rip.
So the current thinking is we don't know now, or what?
Correct, we don't know. Yeah. I
Awesome.
don't know.
Well, thank you so much. Great job. Wonderful. We're very grateful.
And now